Any questions before we get started?
How was the weekend?
Good. Went by pretty fast. How about yours?
Busy.
Busy. Did anyone register for classes? I think new week, new crop of people get to register or something. So I'll just put a reminder, don't forget to register. I've already gotten one email with somebody's registration, and so I'll probably put an extra credit column in Blackboard to keep track of that. So when you register, just email me. Or like we discussed, if you're not registering, if you're transferring, if you're taking time off, whatever you're doing, just send me a little note so you can get your points. Any other questions or comments? Does anyone need to make up a lab in here? Do you need to make up a lab?
Yeah, last week Wednesday.
I'm trying to remember what lab that was.
Catalysts.
Which one? Like with the potato and the energy, that one? Anybody else? Just one person? So probably looking to the week of Thanksgiving. I know that I told my CHEM 221, they're doing their makeup, I think that's November 22nd. So if it's just one person, I may have you tack on with them. Otherwise, that leaves us with, I guess that would be the 23rd, but I don't know if people are like starting to travel or anything like that. So we'll have that tentative the 22nd then, unless more people tell me they need to make up. I was just thinking about it. Do we have class on Wednesday?
Something special on Wednesday?
Oh, I was just looking at Thanksgiving week. Is anyone planning on like leaving and being out of town on the Wednesday of Thanksgiving? So I was just planning on having normal class because we have the acids and base chapter. So we'll probably want the 2 days on that. I just wanted to make sure that half the class wasn't going to be gone or something. All right, let's start with the chapter then. So chapter 7 is now the gases, which may answer some questions that maybe were in the homework of Le Chatelier's principles of pressure, but we'll get to that. And so this is just a quick recap of our states of matter, solid, liquid, gases. And so we said that the solid has a fixed shape and a fixed volume. The liquid, well, now the liquid has a fixed volume, but takes whatever shape it's in. So we have your coffee, we know you can pour it, it'll take the new shape. But now a gas will just expand to fill the container. And so we use the term that gases are compressible. And we could also say no fixed volume, no fixed shape. And so now let's look at a gas and how we kind of treat gases. And so gases, like we've been looking at, so this is just a phase of matter. And so now this is a phase of matter, though, where particles are moving randomly and very fast in the container. And so we have this kinetic molecular theory, and this just allows us to describe how gases move. And so from our kinetic molecular theory, we say that gases move in straight lines. They're just moving in some sort of unperturbed path until they collide with a wall or another particle, and then they bounce and continue off. And so anytime then that you have this collision, so your gaseous atom or molecule, it exerts force, and so it's hitting, for example, the inside of this container when it collides with a surface or other gaseous particles. So then it's those collisions that are where pressure is derived from. And so think of it as a balloon, or if you have a balloon, what it takes to keep that balloon inflated. So there's our balloon. And so, of course, it has the pressure of the atmosphere pushing down on it. And so pressure is, of course, just a force exerted per area unit by the gas molecules. And so, again, on the outside, the air is colliding onto the balloon. So then the question is, well, how does that balloon stay inflated? Well, that must mean that you put in enough molecules of air, at least if it is inflated, that, of course, are having collisions and holding itself up against the force of the atmosphere. And so that's keeping your balloon inflated, all that pressure. So again, that's just force divided by area. And so gas pressure is a result of the constant movement of the gas molecules and their collisions. So again, just think about that movement, those molecules physically hitting and striking the surface. And so that means that the pressure depends on several factors. So of course, the number of gas particles, but then it also depends, well, what volume of a container did we put those gas particles in? So of course, you could put 1 mole of gas into 1 liter versus 20 liters, and that makes a huge difference on the pressure. And then of course, average speed of the gas particles. And so speed is going to be related to temperature. So we're kind of seeing that. We increase the temperature, we increase the molecular motion, the average speed, and that increases the energy. And so we also make some assumptions with the gases, and so we're just trying to treat this as an ideal gas scenario, and what we mean by that is, so according to our kinetic theory, is that we say that collisions of gas particles with each other and their surfaces are elastic. And so again, this is more of an idealized approach, so we're not taking into account any intermolecular attractive forces between them. We're just saying, okay, no energy occurs. So we'll see when this breaks down. And so the exchange of energy, if it were to be inelastic, then that would result in the exchange of energy. So that's not, again, not what we're looking at, but this is, of course, what happens in reality. So again, this kinetic molecular theory is just kind of an oversimplified view of molecules and the gas molecules. So how do we measure pressure? What are the units? And so this is a manometer, a mercury manometer. And so of course you can imagine all your molecules of air striking the surface of that. And so this is all a big pool of mercury, and then this tube here is under vacuum. And so that means all those collisions striking the surface of the mercury, that's going to drive some mercury up into the glass tube. And so this, the amount that it is raised depends, of course, upon the pressure. So, of course, greater pressure, more collisions, the higher this will go. And so this corresponds to our pressure. And so we have different units. So obviously millimeters of mercury is going to be one of them. And so 1 atmosphere is 760 millimeters of mercury. Or sometimes we also use this unit a lot, torr. And so if you notice, torr is the same as millimeters of mercury. And then you commonly also see ATM, or atmospheres. And just 1 ATM is about what we're at. So that's your standard. So here are just more units of pressure. So you probably see PSI with like your car or something. So your car tires are usually around 33 PSI or so. So 14.7 is 1 ATM. Then we had torr, or millimeters of mercury, so equals 760 millimeters of mercury. You may see inches of mercury, especially if you're looking at something like an American unit, or bar is also used. So if you go look up like your local weather report, it may give you the pressure in bar or something. So you just have to watch out for that. All right, so now we'll look at these basic properties of gases and then do some equations with them. And so there are four basic ways we can describe a gas. So of course we can describe its pressure, so high pressure, low pressure, and most commonly we're going to be in ATM. So we'll find that we'll need this for the ideal gas law, but I'll point out when it matters, when it doesn't. And then volume, generally in liters, again for the ideal gas law, but if you're just comparing some ratios, you could be at different volume. Now temperature, this one is always, always, always in Kelvin, especially for these calculations. So star it, whatever you need to do, flag it on your periodic table. So anytime you do these gas calculations, you should always be in Kelvin. And this goes back to just the thermodynamic relevance of Kelvin. So what was Kelvin based off of again? Or even like, what's the range of the Kelvin scale? What does it start at? So negative 273, that's related to the degrees Celsius. Yeah, so 0. So it starts at 0. And so that's the key point, is that Kelvin never goes negative. So in your equations, it will work out quite beautifully. And so good job if you said it's based off of absolute 0, so I'm just emphasizing that. So we said that was absence of molecular motion. Obviously this is kind of theoretical, can't achieve it, but for all our calculations, we're going to need Kelvin to be some sort of positive number. So we're going to need it in this Kelvin scale. So just remember that. Always, always, always in Kelvin. That's the one time the units really do matter. And then moles, so if we're looking at moles, then we just have our N for moles. And so what we're going to find, and maybe you're probably already seeing this, is these properties are interrelated. So you can think of that with the balloon, right? You start blowing air in, so you're adding moles, but that means you're also adding pressure. And of course, that pressure also depends on the temperature. And so we'll start with the simple gas laws, but then we'll kind of look at the overall gas law and how to relate them. And so these simple gas laws just describe relationships between pairs of these properties. And so how it started is we have these simple gas laws. And so Boyle was one of the first ones to start kind of investigating these different properties. And so he used a J tube, which is just a sealed little tube. And then you can take it at different pressures. So your J tube, you can hook it up to something, pull a vacuum, and then measure, well, what's the volume of your gas then at those different pressures. And so he discovered an inverse relationship between volume and pressure. So inverse meaning if volume increases, pressure has to decrease, or vice versa. So if volume decreases, pressure increases. And so looking at this little experiment here, started off initially with 1 liter of a gas at 1 atm of pressure. So there's our piston allowing us to change the volume. And so putting a 2 kilogram mass on that, of course, lowers our piston. Now our volume decreased by 1/2 and our pressure increased by that same factor, so it doubled. And so then we have this that says the volume of the gas is inversely proportional to the pressure. So of course, decreasing the volume forces the molecules into a smaller space, and those smaller space meaning you're having more collisions, so now you have the same amount of molecules in a smaller volume, so now they're going to have increased collisions, which of course increases the pressure. Now looking at this graph, what kind of causes it to plateau out here? What limits it ultimately?
There has to be some volume, you can't hit zero.
Yeah, exactly. So there has to be some volume. Eventually we do reach the physical limit where, if you're having a gas, you're essentially packing those argon molecules or whatever gas molecules next to each other, and then you just simply can't compress them any further. So once you're at a liquid, right, there's nowhere else for it to go. And so now we have this relationship. So our pressure times our volume is always some constant, or we get this relationship. So the equation you'd want to use is your initial pressure times your initial volume is equal to your final pressure and your final volume. And so in this case, you could use different units of pressure and volume, so it would not have to be ATM, as long as the pressure and volume units are the same. So, right, you could use torr and torr, millimeters of mercury, inches and inches, or bar and bar, as long as they're the same between one another. Does that make sense? So same thing with volume. You could use milliliters, that'd be fine. Cubic inches, as long as you're comparing the same thing. So I'll just add that can. Use different volume and pressure units. All right, so all that's saying is use the same unit as volume 1 and volume 2. So obviously don't switch between liters and milliliters, that would not work, but here the units don't matter as much. And so now let's see kind of the physical relevance of this. So has anyone ever gone diving in here? Oh, so you've gone diving?
I got certified last year.
Oh, that's awesome. All right, so tell us about diving. So what happens when you go deep? Why do they tell you you have to rise slowly?
You have to rise slowly because of the oxygen levels in your blood, and then also as your tank empties, it gets lighter because there's less air compressed in there. And so then as you rise, you have to be careful not to oxidize sheets to the surface. You can't mess up your blood.
So then how could it mess up the blood? Take it further.
The oxygen molecules expand, I think, and it can clog your veins, maybe. It's been a minute.
Yeah, I mean, that's essentially it, is you would just deoxygenate or any gas too quickly. So let's look at this. So we'll look at this little diver scenario. So it says for every 10 meters of depth, a diver experiences approximately 1 additional atmosphere of pressure due to just the weight of the water. And so it says if at 20 meters, the diver experiences 3 atmospheres of pressure. And so, of course, what happens to the volume of air in the lungs? And so in your lungs, if the pressure is decreasing by a factor of 3, then the volume could expand by that same factor. And so that could potentially cause damage. So like she was saying, right, if it's releasing too much gas in your bloodstream, that could harm you and cause like bursting and damage. So you have to rise slowly, and then of course exhale, just keep breathing, get all that out. So pretty interesting. All right, let's try this quick problem here. So as you breathe, you inhale by increasing your lung volume. So a woman has an initial lung volume of 2.75 liters which is filled with air at an atmospheric pressure of 1.02. If she increases her lung volume to 3.25 liters without inhaling any additional air, what is the pressure in our lungs? So just imagine, right, if you could stretch your diaphragm and not open your mouth, what would that new pressure be in your lungs? So give me some answers and then, so did we set this up? So our P1V1 equals P2V2, and we just have to be careful to read the problem and make sure we identify P1V1. So okay, we had our initial lung volume and our initial pressure, and then our V2, so we increase our volume. Question is P2, so I just rearranged. So what do we get for P2? 0.86 ATM, is that what you got too? So 0.86 ATM. And so just thinking about how our lungs work, that makes sense. So if you, of course, drop the pressure below the atmosphere, then that makes sense why air would want to come into your lungs now and, again, allow you to breathe. So now our next relationship is Charles's law. So examining our volume and temperature relationship. And so now we find that the volume of gas is directly proportional to the absolute temperature. And so again, absolute temperature telling us that we have to be in Kelvin. And so what we find from our kinetic molecular theory, when we increase the temperature of the gas, then of course that increases the speed. And then if the speed is going faster, that's going to contribute to a greater average kinetic energy of those particles. And the greater volume spreads the collisions out over a greater surface area so that the pressure is unchanged. And so this is saying that we're holding basically our pressure constant. So if we want to hold our pressure constant, And again, increasing the temperature, we're going to have to increase the volume then to account for that. And so now this is Charles's law graphically. And so some of this is extrapolated down to absolute zero. So of course, the gases in reality condense to liquids, but you can just see this relationship. So again, increasing volume as our temperature increases. So volume, temperature, and then this is just for different points. So holding steady at 1 atm and 0.25 moles, 1 atm, 0.5 moles, 1 atm, and 1 mole. And so here's just another example, and I'll find it, while we look at this, let me queue up a YouTube video. So the YouTube video is going to show a greater difference of this, but if looking at this little balloon, so if you have a balloon and then you put it into a bunch of ice water, so now it was a nice regular balloon at ATM, normal room temperature. Now we've cooled it, so now those molecules inside have a lower kinetic energy, so of course they would slow down. Now thinking of the atmosphere, right? So the atmosphere is beating down on that poor balloon, and so with that decreased kinetic energy, the balloon shrinks a little. And so of course if we look at the same thing, so now just taking that same balloon and putting it into boiling water, of course, increase the kinetic energy. Now, increase kinetic energy, that gives us more pressure, and so that volume increases. Let's look at this.
Hi everybody, I'm meteorologist Jay Burschback along with Carl Nelson at the Imagination Station. Today we're dealing with one of my specialties, air pressure, the power of air pressure. And you may have seen this experiment before using a gas can or a smaller can. This is big scale. This is the Imagination Station's version of supersizing that experiment, showing air pressure which can crush this huge barrel. Carl.
So we got a steel 55-gallon drum here. And I just want to give you a sense for how strong, how rugged these barrels are. Jay, if you could stabilize the barrel. I'm going to take a sledgehammer and try to... If you relied on me to crush this barrel, we'd be here all day.
Sure.
That thing is pretty tough. So instead, like you said, we're going to use air pressure to crush this drum. So let me flip this up. I'm just going to stick it on its end here.
On its end? Oh, okay.
Because what I'm going to do first is add some water inside. About 6 cups of water. And what the water is going to do is we're going to create water vapor inside that we're going to heat up. Now water vapor when it's warmed up and air when it's warmed up occupy a little bit more space. Our goal is to try to trap some of that expanded air and water vapor inside. We're going to seal this up and then cool it down.
Okay.
We should see some crushing action at that point. But first, we're going to need to heat that air up.
Okay.
So help me flip this up on our stand here.
Okay.
The thing we're looking for, Jay, is we want to see a nice solid stream of steam coming out this opening here.
Sure.
And in order to do that, we can't just use like a blowtorch or anything small. As this is the supersized version, we're going to use one of these road torches.
Yeah, I think I'll back up.
All right. So it'll take a few seconds here to get the water warmed up inside the barrel, but to give you an idea how big the flame we're going to work with. See, there's a good sort of jet of steam shooting out, but we're going to try to capture that by putting the plug back in. We're going to wrench it down tight because we don't want any of that warm, expanded air to escape. But the key now, Jay, is wheel over that tray of ice. We're going to cool this baby down really quick in a tray of ice. Hold on. I'm going to spin it down. Well, the first thing we should hear are a couple of ends of the drums popping in.
There we go.
A couple of the ends going in. Give it a second.
So what we're seeing is air pressure literally crush.
14.7 pounds per square inch of normal atmospheric pressure are now pushing down on this drum, and because that water vapor inside and that warm air inside
There it
has
goes.
cooled down, taking up less space, doing a lot more damage than that sledgehammer did earlier.
That is
to the drum.
amazing. Looks like a pop can or a soda can.
Looks like a pop can or a soda can, or if you ever rinsed out plastic milk jugs,
Sure.
and then you put the cap back on with warm water, stick it on the counter, you can see after a time they start to like collapse back in. Same principle, but it's a safe, at-home way you can do it.
Sure, yeah, no one.
Have you all noticed that with the milk jugs when you rinse them out? Yeah, so same thing, so you've seen it. And so there, right, they did kind of the same thing, it's just they heated up all that water vapor, so they had it all in there, high energy, but then they closed it, and they probably had, you know, less moles, and some of it escaped out as steam, so then they trapped it all, and then cooled it back, and of course you saw how it crushed down with, again, that weight of the atmosphere just beating down on that drum. And then, of course, they cooled down the steam, probably went back to water, and so no more vapor to hold it up. And so now let's look at the math. Oops. So the equation that we get for our Charles's law is now V1 over T1 is equal to V1 over T2. And so now this is telling us, so volume and temperature have a direct relationship. So meaning, in this case, so if temperature increases, and remember, we're holding pressure constant, so holding P constant in all these scenarios. So if your pressure is constant, but your temperature increase, that means your volume is going to have to increase too, again, to hold that pressure constant. And so same thing, holding pressure constant. If you decrease the temperature, if we want that pressure to stay the same, then our volume also has to decrease to compensate. And so now let's practice our problem here. So a sample of gas has a volume of 2.8 liters at some temperature. So you submerge the sample in ice water to 0.00 degrees Celsius. Its volume decreases to 2.57 liter. So what is the initial temperature? So don't forget to convert. let's see, do we set up, so V1 over T1 equals V2 over T2. And so what do we have to convert our temperature to? So what's our degree in Kelvin? So 273. And so now we can plug stuff in. So liters, so we don't know T1 is equal to, so V2, 2.57 liters over 273. And so now we can just cross multiply and solve. So 2.8 times 273 divided by our 2.57. So what do we get for this in Kelvin? So do we get 297 Kelvin? So I see some nods, other nods, thumbs up. I saw another nod. And then, so how do we get back to Celsius now? So we have Kelvin, 279. So minus 273. And so that gives us back to 24 degrees Celsius or so. So everyone, oops, get that one? Some more nods, sweet. So the next little direct relationship we'll look at is this Avogadro's relationship. And so this one's, again, pretty self-explanatory. This makes sense. So volume and moles have a direct relationship. And again, we're holding our pressure constant in this scenario. So pressure and temperature are constant. And so that means, of course, if we want to hold the pressure the same, if we keep increasing the amount of moles, then obviously the volume is also going to have to increase to accommodate that. And so volume is directly proportional then to the number of gas molecules when pressure and temperature are held constant. And so this makes sense, of course, if your moles is increasing, so N is your number of moles, if that increases, obviously your volume will have to increase as well, again, if pressure is constant. And same thing, so if your number of moles decreases, then your volume will also have to decrease, again, to have that constant pressure. And so here's a really key factor. And so equal volumes of gases contain equal numbers of molecules. So identity doesn't matter on the gas here. So if you're just talking about volume, so they contain the same amount. And so this gives us our relationship. So V1 over N1 is equal to V2 over N2. And so this is, again, kind of what we've seen, repeating things. So we just said that the volume of gas has to be directly proportional to the number of gas molecules. And so we've seen that, of course, if we increase the number of gas molecules, that's going to cause more of them to hit the wall at the same time, so increasing our pressure. And so to keep the pressure constant, again, our volume has to expand, so we have a greater surface area, bringing our pressure back down. All right, so let's look at this question. And so we have a male athlete in a research study has a lung volume of 6.15 liters during deep inhalation. And at this volume, his lung contains 0.254 moles of air. During exhalation, the lung volume decreased to 2.55 liters. And now watch the question, how many moles of gas does the athlete exhale? So take a minute to try that. And again, don't forget your formula. So V1 over N1 equals V2 over N2. So let's start hearing what y'all did. So just setting up our problem initially, so 6.15 for our volume, 0.254 moles is equal to 2.55 liters over X. Oops. So then we can solve for X at least, so 2.55 times 0.254 divided by 6.15. And so do we get this 0.105 moles, but then in the lungs? So 0.105, so in our lungs. But then the question was asking how much does he exhale? So how much did he exhale? So we had to subtract to figure that out. And so should have gotten 0.15 moles roughly. So I see some nods. So just make sure, again, read the problem, see what it's saying. And so it's asking again, exhale, we can only calculate what's in there. So we have to subtract. So 0.149 moles exhaled. Oops. Oh, that was weird.
What did you subtract again?
I just subtracted. Man, I wish the whole thing hadn't.
So it was, I know it was the last number, but you subtracted, was it like 273? Or?
It was 0.254 minus that. So we had solved, so our new N2 was 0.105, so we said in lungs. So then we subtracted just that initial 0.254 minus how much was in the lungs. There we go. All right. Any questions about just our simple laws and relationships? And so now this brings us to the ideal gas law. And really, this is all you need to know for this chapter. So PV equals nRT. And so you can actually derive everything from this. So let's just look, first of all, what's PV equals nRT, and then how do we get back to all our other laws? So of course we saw P is pressure, V is volume, N was moles, and now R is this gas constant. And so this is where the units matter. And so now pressure has to be in ATM, volume has to be in liters, N is in moles. And so R gives us, so this is the ideal gas constant with these units. So if you go into Google and just type in like gas constant, or ideal gas constant, you'll get a bunch of answers. And so why that is it's just for different units, so be warned. So I would stick with these units, so therefore you can always use this 0.0821. Again, that's liters, ATM, and then Kelvin. And so just looking, so if you do ideal gas constant in Wikipedia, it gives you a bunch of stuff. And so that is all for the other unit combinations. So here's the one that we like, liters ATM, moles torr, so 0.0821. That's the one that we use. But again, you can just get a flavor if you have a different unit, get a different gas constant. So that's where all those come from, so don't let that confuse you if you see it later. And so now let's see, well, how do we derive our other laws from this? So if we start with PV equals nRT, so then we can rearrange our equation. So if R is just a constant, we can set our equation to R equals PV over RT. And we can just call this P1, V1. Oh, I don't know why I put N. That's supposed to be NT. So N1, T1. And so let's say, so we said that's equal to R. And so this means, though, that we could set this equal to another set of conditions, right? P2, V2, N2, T2. And if R is just a constant, then we can just set them equal to each other. So now we're at P1, V1 over N1, T1 equals P2, V2 over N2, T2. And so I like this form too. So this is kind of like the ideal gas law all combined formula. And so you notice like N and T, all these will start canceling as long as you hold them constant. So if we go back for a second. So if we go back to Boyle's law, so we were just looking at changing volume and pressure. And so, right, we have P1, V1, N1, T1, P2, V2, N2, T2. But then for Boyle's law, right, N is constant. So in this equation, that would cancel out. T is also constant, according to Boyle's law, so that cancels out. So that leaves us back to our P1, V1 equals P2, V2. So that's very convenient. So I like this form. So again, this is good, especially if you're changing like 3 variables or even all 4 variables. This would be the equation you use, again, just canceling out whichever one is constant. So the other thing you get, and what kind of helps you remember from our ideal gas law. So if you have the variables on the same side, so P and V, that means that they're inversely related. I probably misspelled inversely. So they're next to each other. So inverse relationship. And then we had said that volume and moles and volume and temperature of those were both direct relationships, and that makes sense. So looking at this equation, so volume and temperature then have a direct relationship. So opposite sides of the equation, volume and moles. So again, we see that direct relationship. And so you could look at other relationships too that aren't explicitly covered. So moles and temperature, that would be considered like a inversely related. So if you're holding pressure and volume, the same. If temperature increases, you have to decrease the amount of moles then to stay that constant pressure and volume. And so pressure and moles could also have a direct relationship. So if your volume is being held constant and you're increasing your moles, that means your pressure is increasing. That really helps you with all of that. And so this is just showing the same thing, just another way to see the derivation. So of course, they just pulled it out individually with those constants, and you get back Charles, Boyle's, and Avogadro'S law. So let's try this little sample problem. So calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atm and a pressure of 315 Kelvin. So then the question is, are you using PV equals nRT? Are you using the combined gas law? So which one's appropriate for this scenario? And then of course it's plugging in all the variables. Let's see, so which equation did y'all pick? So the top one or the bottom one? So top one, so we don't really have like final initial conditions, so this looks to be the good one, or the appropriate one for this case. And so you can always just write out what do we have. So we have pressure, that's an ATM, so that's fine. Temperature, they gave it to us in Kelvin, so that also looks good. And so we're looking for volume. We have moles. And so it looks like we're ready to plug it in, and we just need, so our R we said was 0.0821 for our gas constant. So now it's just plugging everything into our equation. And so what do we get for the volume? Oh, man. So is this what people got for the volume? So I see some nods, so about 15 or roughly 16. And then what's the unit on this? Liters, exactly. So that matches with our equation. Back to our constant too. So we said our 0.0821 was liters, ATM, Kelvin. So that means that this volume is in liters. So 15, about 3 sig figs, so 15.95, so rounding us to 16.0 liters. Good. Any questions on this calculation here?
How do we know which one's the constant on that one?
So the constant is just the R, and so R is always 0.0821 for the liters ATM Kelvin. Yeah, so just going back to here, use the constant and make sure you're in ATM, liters, moles, and Kelvin, and then you're all set to go.
So it's always going to be the 0.821.
Yeah, as long as you're in liters, ATM, Kelvin. So you might see other gas constants, and that will be for like other units or something. All right, so let's look at the standard conditions. So STP, and so this is used a lot either in reference materials, so you always have these STP conditions, so you can do the experiment at the same condition and come up with your constants. And so all this standard condition is saying is that we're at 1 ATM, and then 0 degrees Celsius is our standard temperature. Standard amount is 1 mole, and then this is really key. And so at STP, our volume is 22.4 liters. And so looking, this is again the volume occupied by 1 mole of the substance, and this is so any substance. Again, just make sure you're at STP conditions, so it would say that STP, so you know you're at 273 Kelvin, and you know you're at 1 ATM, and again your volume 22.4 liters. And so just like we had said in our couple of other slides, when we're looking at our gas laws, so we said that the identity of the gas doesn't matter, so it doesn't matter whether we're looking at 1 mole of hydrogen or 1 mole of xenon gas. With our kinetic molecular theory, right, we don't care about the size at all. We're not looking at the attraction between them or anything. We're just kind of looking at the basic facts. or factors here. And so that means that 1 mole of any gas will occupy 22.4 liters. And so this does generally hold, again, for these STP conditions. So of course we mentioned at the extreme conditions, that would change since of course hydrogen is just physically smaller than xenon. But at these conditions, we can treat the gases like this ideal gas, like we've been treating it, so no intermolecular forces, and so it all occupies 22.4 liters. And so they would have different densities, and so that's kind of what they're hinting at here. So we have 1 mole of different gases, they all have different masses, even though they have the same volume. And so, of course, density is mass over volume. So let's just say, let's calculate then the density of each of these gases. So take a minute or two. So how would you calculate the density then of these gases? So see if you can calculate that. So what do we get for the density of helium, or how do we calculate it?
We use the atomic mass.
So what's 1 mole of helium weigh, or? So 4, and then divided by 22.4 liters. So this has a density of 0.179. And so that would be grams. Oh, so this is just from the periodic table, from the mass of helium. I think I forgot a periodic table. See if you can see the back wall. Otherwise, I'll pull up this one so we can see. So helium has a mass of pretty much 4. And so now xenon, so what's xenon's density? Or maybe what's its mass? 131.293. So divided by our STP, 22.4 liters. so xenon now has a much greater density, right? 5.86 grams per liter. And then our last one, so methane. So what's the molecular weight of methane? Yeah, 16, so that's pretty good. We don't have to worry too much about rounding. So 16 grams divided by 22.4. What does that give us? And it's now 0.714 grams per liter. So again, you can see density varies greatly, but they're all 22.4 liters. And so something else that you might see with this, so now we can ask, so at STP, what volume does 0.0556 moles occupy? And so kind of the easiest way to approach this problem is with a proportion. So you can always set up, so 1 mole, you know, is 22.4 liters. And so if I have 0.0556 moles, that would be X. So then you can just cross multiply and solve. So 0.0556 times 22.4. And then that gives you your answer. So divided by 1 gives you 1.25 liters. So that's a lot easier than trying to go like moles to something else, so moles to volume and all around. All right, let's stop there, so I don't want to do. So I have homework, so I'll pass out homework. Yeah, it'll be a quiz, so the quiz be over energy.
Here we go.
Was there anything we needed to recap with last week's chapter, energy, before we take the quiz? Yeah, I would go ahead and ask now. So yeah, we'll just recap. So making bonds, like you were saying, so that makes energy. So then we said that that's exothermic.
Oh, my question was, I remember now. If it's like making energy, it like needs more energy to like make something. So wouldn't it be any of them because it's like taking energy more energy?
So do you mean like the overall process? Because you have like two separate things that you're looking at. So you said making bonds, right? That's exothermic, but then you have to take into account whatever you're breaking. So that's endothermic. But then that's where you add the two numbers together, and I don't know if this is your question, but then you get, right, your overall sign for the process. So bonds making plus bonds breaking, and then that gives you, yeah, so then if it's positive, then you say it's overall endothermic, or it's overall negative, where that would mean some sort of exothermic reaction. But, and I don't know if this is part of your question, because, you know, we talked about catalysts. So you could have a reaction that is formally exothermic. So, right, you have some reaction, maybe it looks like this. So that would be exothermic, just because the products are lower in energy, so energy release. But then maybe, though, this activation energy is so high that the reaction doesn't occur. So that could happen. So we're only looking at like the energetics part of it, so only like the thermal part, but we're not taking into account, you know, the activation energy. Is that really difficult to achieve this, to get to whatever transition state needs to happen? And so that's your transition state. Did that answer your question? And so I got some great questions by email too about how pressure changes the reaction rates with Le Chatelier's principle. And so with that, I think basically the concept was, so if you have the fixed number of moles, but if you decrease the volume, right, that would increase your rate. So if you had, you know, just thinking about your balloon, if you have some sort of gas phase reaction and then you shrink it, then you're going to have more collisions in that tighter space. So then you should have more productive collisions too, so that should hopefully increase your reaction rate. And so same thing with crushing. I think we did that in lab. Maybe we didn't. But if you increase the surface area, that also tends to increase the reaction rate. And so like zinc metal, for example, like that would not do anything. It probably slowly oxidize over time, but it's pretty unreactive. But then zinc powder is considered flammable. I've never seen it go up in flames with my own eyes, but I've heard stories that yes, you know, if you do have this fine powder, it could actually be flammable. So that's where, you know, increased reactivity, increase in hazards too. Right. Other questions or concepts we need to touch about before the quiz? I don't think the quiz should be too difficult. There's one energetics question, and then the rest are mainly kind of definitions. All right, let's go ahead. I'll let you take your 10-minute break, and then we'll start our quiz once everybody gets back around 10:25 or 2:25 or so. And I will go ahead and stop this recording.